Good evening, students. Welcome to another session of advanced classes. And till now we covered physical topics. Now we are seeing some organic topics. The first one, the basic organic chemistry, we just say mainly as general organic chemistry, where these topics like isomerism phenomenon, electronic effects, the application of electronic effects, and stability of intermediates, and the acidic and basic strength that we generally cover under this GOC, which is, let us say, like a base for organic chemistry. So if anybody is thorough with the GOC, they can do, let us say, like wonders with this organic chemistry if you are strong in the GOC. So let us see the concepts we cover, like what we have done already, like previously. The true statements, there is some error in P and Q. So these are like mostly maybe like multiple answer type. Okay. So what is the given thing is there is a Neumann projection that are given for the particular compound. So this is like an amino alcohols. There is NH2 group and OH group. So for this, the P structure and the Q structures are mentioned. And what we call these structures as, actually, we say these structures as a Neumann projections. And if these groups at the first front carbon and the back carbon, they are at an angle of dihedral angle of, let us say, 60 degrees. We call such type of structure or representation in the Neumann projection, we call these representations as staggered representation, or let us say like a partially staggered representation or fully staggered representations. But when we just say that Gaussian forms, which are nothing but called the partially staggered forms, this is like a what we call it as a partially staggered forms, where the bulky groups like OH and NH2, they are just adjacent like this, are at an angle of 60 degrees. But in this now, where these OH groups are, OH and NH2, bulky groups are completely opposite. So this is, we call it as completely anti-form, fully staggered form. This is the partially staggered form or a Gaussian form. So the usual way of saying it, let us say, instead of seeing this only, let us try to cover little bit regarding this, what we call it as conformers. When we say bulky groups are there in a conformers, what we write, conformations, what we write, if it is exactly the groups on the front and back carbons, when they are on the same. So the bulky groups like suppose A and B are, let us say, a bulky groups, when they are completely one below the other with a dihedral angle of 0. But we are to represent it, we are just writing just a slide. So what we say, the between the bulky groups there is electron cloud repulsions. So there is a steric effect also exist, or steric hindrance exist. And between this bonded pair of electron and the bonded pair of electron and the front and back carbons, there will be a bonded pair repulsions also. This bonded pair repulsions we say generally as a torsional strain. So this is steric strain, and this electron cloud repulsions, bonded pair repulsions are nothing but called torsional strains. But if it is, let us say, like a staggered conformation with an angle of 60 degrees, when the bulky group is coming, suppose A and B are coming at an angle of 60, then the steric repulsions will decrease as well as torsional repulsions will decrease, because the bonded pair electrons are at an angle, are away from one another, and the bulky groups are also away from one another. So their electron cloud repulsions also will decrease. So that we generally say this is a staggered. and this is eclipsed. But we say staggered with a less repulsions, torsional repulsion as well as steric repulsions. We say staggered conformation is more stable than eclipsed conformations. So when you have bulky groups completely, and if the bulky group and the hydrogen or smaller groups exist with a let us say that is called partially eclipsed forms, we say they are more stable than the fully eclipsed conformation. So this is like a fully eclipsed. But if it is a partially staggered. But if you write completely opposite groups, A and B completely opposite, then we say it is a fully staggered or completely anti-form. Then we will say anti-form is more stable than partially staggered or Gauchy forms. But when the groups are having some interactions there, then we say there can be the attractions between the groups, then the staggered conformations sometimes like partially staggered conformations generally sometimes can become more stable compared to antiforms. So whenever there is a general interaction, is nothing but between the groups is a hydrogen bonding repulsions. That is what we generally have. So when we see this OH group and NH2 groups, so what we see, the options, suppose you just see the OH group and NH2 groups, between these two, there is a hydrogen bond between the hydrogen and nitrogen as well as the hydrogen and oxygen here. So hydrogen bonding can exist here in the P. But in Q, because these OH groups are quite completely opposite, there is a hydrogen bond, but not between within the molecule. It is molecule to the molecule, it may be there. So this is nothing but what we call it as intramolecular hydrogen bonding. But this is like an intermolecular hydrogen bonding that can exist because there is a possibility there is a hydrogen which is a delta positive hydrogen and more electronegative atoms like nitrogen and oxygens are there. So it can show hydrogen bonding also. So, but this intramolecular hydrogen bonding mainly stabilizes this compared to that. So we say, as you see the options, first one of this option I can select it. P is more stable than Q. But let us see this option. P and Q have equal torsional strains. But not if you see this bonded pair repulsions, which we say like a torsional strains. So the bonded pairs are completely always at an equal distance, whether it is in a P form, whether it is in a Q form. So we can say the torsional strains are same in P as well as in Q because the bonded pairs are at an equal distance. So this is also true. Clear? Then coming to this, P has higher dipole moment. So among this P and Q, P has a higher dipole moment. So with O and H group, NH2, what will be the possibility? So let us see this in the next slide, the basic structure of OH and NH2 here. So if it is taken with the P structure, what we have to check. So we have a OH group here. So with an angular or V shape and NH2 here. So it is like a pyramidal. So this is N, H, H. You can write 11 pairs. Or simply you write NH2. So there is a bonded dipole moment. This bond dipole moment exists like this. This O and H dipole moment exists like this. So they are not opposite anyhow and they are working like this. So the net dipole moment between these two, if you just extrapolating this, you will see the net dipole moment exists in this direction. But both are working or both are acting in the upward direction. So the net dipole moment mu net value for the P value exists like this. But when it is a Q, then it is OH group is here and NH2 group is here. So you can say the dipole moment exists here like this Here the dipole moment exists upwards. You just only take this OH groups also and NH2 groups directly. So this dipole moment exists like this dipole moment exists like this. So here the dipole moment is like this in case of OH group. In case of NH2 it is like this. But here the net dipole moments here are existing or acting opposite to one another. So here the dipole moment of OH will oppose the NH2 and simultaneously the NH2 is opposing the OH. So when we compare these two, mu net value for this compound and for this compound, mu net value for both the compounds is not equal to 0. Both will be having net dipole moment because the groups are also not same, and even if it is a OH group, then also it is having a net dipole moment, because when we usually written here with the, suppose assuming this NH2 as a OH group, but the net dipole moment is not in this direction with the OH, it is acting like this. Here the NH2 is acting like this. That is, we have some questions on a benzene ring, suppose there is a OH group. Similarly, OH group. The net dipole moment of this molecule also will not become 0. Because of this OH group, which is in a para position, will act in this direction. This will act in this direction. So there is a net dipole moment. There is completely not opposite to one another. But if it is atoms like Cl, so when we have Cl here and Cl here, the net dipole moment of because of this, the net dipole moment of because of this acts completely opposite to one another. Because it is a linear atom or a single atom, it is existing in this direction only. It is existing in this direction. The net dipole moment of this molecule will be, this is a mu1, suppose this is also mu1. So mu, both the dipole moment values are same because of it is carbon chlorine. This is also because of carbon chlorine. So mu net value here becomes equal to 0. But in this case also, mu net value is not equal to 0. So what we say here, the net dipole moment acts in the upwards direction. But here the net dipole moments are acting in opposite directions, in an anti-conformation. So that the net dipole moment of P will be greater than, or if you say this as mu1 and if you say this as mu2, we say mu1 is greater than mu2, or P has more dipole moment than Q. So what we see, this options now. This P has a net higher dipole moment. This is also true. And this is given like a Q is the least stable form of this compound. This we say is less stable than the P. But comparatively Q is less stable compared to P. But Q is not the complete, means anti-form is not completely the least stable conformation. It is the fully eclipsed conformation. Because the OH group and NH2 groups, they are completely at an angle of dihedral angle of 0. There the steric repulsions are very high, so that eclipsed conformation, fully eclipsed conformation becomes very less stable. So this D option, which is indicating Q form is the least stable, that is not a correct option. Okay? So this is, let us say the first three options are correct in this case. Now coming to the next. Choose the incorrect statement regarding the following structures. So we have W, X, Y and Z. So the options as W and Y, one the compounds are represented in a different means these are in the Fisher projections. This is in the Sahas type representation. This is in the Neumann's representation. But the relations are asked between W, X, Y and Z. Let us see which is maybe correct and what is we'll see. So CH2Cl H, Br, Cl. So this is like a chiral molecule, chiral carbon. This carbon is also a chiral carbon at this. So this is again the same, but only the Cl and Br are changed, means the Br is replaced with Cl, but at this carbon, so this carbon is also now a chiral carbon at this. This carbon is also a chiral carbon at this. So each compound is having, each molecule, whatever is represented here, is having, let us say, mostly 2 chiral carbons. This carbon is a chiral again, this carbon is a chiral. But in this, the groups at this chiral carbon Br, H and CH2Cl, here also H, Br, CH2Cl. In this also this is CH3, Cl and H. Here also it is CH3, Cl and H. But here it is completely different. The Br is not there, Cl we have there. But at this carbon the groups are same. Now this is again the same. Let us say we have Cl and Cl here. So these two might be interrelated to one another. So this is also having, the back carbon is also chiral. So there are 2 chiral carbons in each and every molecule, what is represented. But these two are indicating the same, because the groups at the particular carbons are same. CH2Cl, Cl and H. Here also the back carbon has CH2Cl, Cl and H. So these two may be a particular relation, they hold. These two may hold a particular relation. But usually, every student point of view, we usually say it's better to convert any compound which might be given in any other 3-dimensional representation. So the general 3-dimensional representations are 5 Fisher projections, we have Sawhorse representations, we have Neumann representation and a flying wedge representation. So for the student point of view, it is better always to convert any projection which is in the other than the Fisher projection. Try to convert into Fisher projection, which is a most easiest way to compare for a student to see whether the optical activity exists in the molecule or what type of relation generally exists. Because when we say the Fisher projection, suppose we say this is a compound. If an open structure is there, if a compound has an open structure, to say a compound to be optically active, what we generally say, there must be this type of plane of symmetry should be absent. One is a plane of symmetry, the second one is center of symmetry, then there should be an alternative axis, there should not be any alternative axis of symmetry. So if a compound doesn't have the plane of symmetry, center of symmetry and alternative axis of symmetry, then the compounds are considered to be optically active. Our compounds are said to be chiral. So to see optical activity in an open chain molecule, what we usually simply say is, or better for the student point of view is, compare whether the compound has a plane of symmetry. If it is an open chain, if the compound doesn't have plane of symmetry in the open chain molecules, then the compound is generally optically active, or compound will be optically active. But if it is a cyclic molecules, just try to check only 2. That is, whether it has a plane of symmetry and a center of symmetry. If plane of symmetry and center of symmetry are absent in a cyclic molecules, then the compounds are optically active. So if any type of symmetry exists, then it is optically inactive. Because in the student point of view, there's checking the alternative axis of symmetry is not that much easy for them. So if it is an open chain molecule, to see the plane of symmetry, it is better we should write in a Fisher projection. Because in a student point of view, they can compare easy again. So what is this is now? If I see a molecule in the Fisher projection, these groups are completely, which are written vertically upwards, they are backside. And the groups which are present horizontally, they are towards the observer. Means these 2 carbons we are holding in a plane. At this carbon, a group is backside. At this carbon, there is a group backside. But at this carbon, there is, means if it is a 2 chiral carbon centers, now we will say, So these two groups are working, acting up or towards observer or above the plane. These two groups are above the plane. So which we can even write like this also. This is a carbon, this is a carbon. At this carbon, the groups which are horizontally, they are above. So with a flying wedge representation, if we use, we write as solid wedges. And the groups which are vertically placed, they are below. They are like this. So if I have a plane of symmetry, we draw a plane of symmetry at this, means if I draw a plane like this, assuming a plane like this, if these groups are same, means the BR is here and the BR is here. So a plane which is passing through between these two carbons, so the groups are suppose same, means if it is Br and this is Br and this is hydrogen, and the back side we have the same group suppose, then the plane is like this. So these groups are completely same. Therefore again we say this compound is having a plane of symmetry. But in this case, do we have a plane of symmetry now? Means if you pass a plane like this, this is Br, this is hydrogen, this is hydrogen, this is Cl, this is CH2Cl, this is CH3. So anywhere it is not symmetry exist, Br and H. So this compound is optically active. So we will say this compound is chiral, because there is one option which is also pointing that. And this one, we have Cl and Cl at these carbons. Even the Cl is here, suppose. Then also this compound doesn't have a plane of symmetry, because this has CH2Cl, this carbon has CH3. So even the Cl is on the right hand side here. Then also the compound doesn't have a plane of symmetry in this case. So this compound is also, we say, simply chiral. So both these W and X are a chiral molecules. Then coming to this, how to convert this Sahar's representation into a Fisher projection representation. So just follow this system. I feel it is a better system we should follow. That is the practice generally we will do. So let us see. If it is a Sahar's representation, let us say we will write in the next page, then we will come back to this. So if it is a Sahar's representation, the groups are suppose represented like this, and at this the groups are suppose represented like this. Suppose it is A, this is A, this is B, this is C, this is B, this is C. Means bring the two carbon groups completely into this form. Let us say like simply Y, a simple way to say, in the Y structure. Even if it is having an inverted Y shape, try to bring them into inverted Y form or Y form suppose. Then if you just hold this molecule like this, means the A group is here, A group is here. If you are holding this compound simply like this, A goes backside, A goes backside. This B which is on the right hand side will exist on the right hand side. The C which is on the left hand side which is existing on the left hand side. Means this if you write simply, this is the representation. That is A is here, B is right side, C, then B, C and E. So in a simple way, this is the way we can easily convert it. So try to bring into Y form. Even if it is an inverted Y, you can do it, but you have to hold the molecule like this. Means this carbon will become a top carbon if you write in the Y form. If it is in this way, then you have to write simply like this. Hold the molecule like this. Means if it is suppose B, C, A, let us say A, B, C. What is this is? Just holding the molecule like this. So what is this? I simply write it. This is a top carbon now. So this will become top. This will become the bottom. In this case, this is the top. So holding this molecule like this. So B, A will go backside. So A, C is on the right hand side, B is on the left hand side, C and B will go backside at this. So C will be right hand side C, and this is A. So this is the simplest way to convert a Sahar's representation into Fisher representation. But anyhow, the staggered form was not there in this. We will see the eclipsed Neumann projection, how we will convert. It's also the same. It's like only just front carbon and back carbon, which is we are seeing this is Sahar's representation. That is only what you are representing in the Neumann. So if it is a Neumann projection also, it is suppose like this. So let us say A, B and C, A, B and C. What we do is, we try to bring this carbon, means this carbon is the front carbon, the back carbon. You are holding this two carbons between this front and back. You are holding the molecule like this. So your group which is on the right hand side will remain on the right hand side. The group which is on the left hand side will remain on the left hand side. But this front carbon will go as a top carbon. So in such case, this carbon will become like a top. So for that, we try to bring both into the same, like this form, let us say like inverted Y shape type. So this carbon also we are rotating. So when you rotate a particular carbon without breaking their bonds, if you are just rotating the carbon or groups at that particular carbon, the configuration of the carbon will not change, because we are not breaking the bond and forming the bonds yet. So what we generally say, the definition of, let us say, geometrical isomers or configurational isomer, conformational isomers and all that. So when you just rotate it, it will not change its configuration. So just rotating that first by an angle of 60 degrees. That is the back carbon we are rotating. So what is this representation now? This is A, this is B and C. But this carbon comes here, that is A, and this B, and this is C. So now holding this carbon, CC bond in this form simply, means your front carbon will go as a top carbon, and the back carbon will come as a bottom. So when you write this in the form of now, as simply like this, A will go back side, C and B, A exist back side, then B and C. This is how we usually try to convert a Sahar's into Fisher or Neumann into Fisher. Let us follow this, or if you are following any particular procedure which is discussed by your faculties, let us follow that. If it was already you have in the practice, or if you follow this and if you feel this is better, you can follow even this. So if you see conversions here, the conversion of a Sahar's into that in the particular case what we had. So let us see the question now. So if at this carbon, now what we try to do is, this carbon is, let us say, like a Y shape, means this carbon, this compound was like this, CH2Cl and H and Br. So at this carbon we are having like an inverted Y shape type. So try to bring in this way, means the CH3 group was below. So try to bring at this carbon also in the Y form, so that the CH3 groups comes at the bottom, means CH3 group comes here. So we are rotating it like this. So CH3 group comes here, then the group says should exist like this. Then what is the orientation of the groups? CH3, Cl and H. So CH3, Cl and H, they are in anti-clockwise direction. CH3, Cl and H. Means you are converting this into suppose Fisher. What is its Fisher form? Means this form and this form is one and same. And what is its Fisher now? CH2Cl, Br, hydrogen, this is Cl, H and CH3. Clear? So this is the Y. This is the Y. So anyhow, we have to compare only these two, W and Y. What is the first option for us? W and Y are diastereomers. So what is meant by diastereomers? Which are not mirror images to one another, as well as which are not superposable to one another or imposable to one another, what we generally usually see. So which are not mirror images as well as not superimposable, they are diastereomers. But if you see these two, at this carbon we are having H and B are same, but Cl and H means if one chiral carbon configuration group C are interchanging once, then immediately it turns into diastereomers. Maybe you have R and configuration maybe, or R and S configuration maybe, but here when you are interchanging at one carbon once, then immediately that carbon from R it changes to S if you are using that absolute configuration. So S configuration becomes R, R configuration becomes S. So you may have suppose R and R, you will see R and S. If you have S and S, you will see S and R. If you have R and S, you will see R and R. So because we are changing only one carbon with respect to that. So we will say W and Y are diastereomers to one another. So this is correct. The next, coming to Z, it's a Neumann projection of X. Yes, because both these are representing the same. So it is a Neumann projection for this molecule, maybe not for the same molecule, maybe it is one of the Neumann projection representation. Maybe if you see even the compound might be same, that might be there also. Let us check that also. So here we have CH2Cl, that is anyhow what we see. But you just write this carb CH2Cl downside, then it is actually your what you require, because you are holding this compound now like this. Your back carbon will become a top carbon, because it is a Neumann projection like this. So it is inverted Y, I said. It is like this, you are converting the front carbon as a top carbon. But now it is, suppose in a Y form, your back carbon should become a top carbon. So let us rotate this carbon simply. So what is its Neumann projection? CH3, H and Cl. Here we will get CH2Cl. Here we will have this CH2 and Cl, and here H. So if you are writing this in the Fischer projection, means holding this molecule like this. So what is its CH2Cl? So CH2Cl and H is here and Cl is here, and this carbon, front carbon will become your bottom one, Cl and H and CH3. So let us see, both these are representing the same, means X and Z are representing the same molecule, even with respect to their configurations also. So what we say, Z is a Neumann representation of X, which is also true. Now coming to this, W, X, Y and Z are optically active. Anyhow, they are optically active because there is no symmetry anywhere. So this W, X, Y and Z, everything are optically active, because at particular carbons the groups are completely anyhow different. In this case it is different, and this is, and these are only just, they are stereoisomers to one another, because these two are, we already said, they are diastereomers. Okay. Now X and Y, X and Z are representing the same molecule, and Y and Z are mesoforms. So Y and Z cannot be meso, because anyhow the groups are not same, they are optically active. So meso is completely having a internal plane of symmetry, or simply there is a symmetry in the molecules, then the compound becomes optically inactive. So a stereoisomer which becomes inactive due to the symmetry, we generally say a mesoform. So this is not correct. So in this case also now A as well as B and C options are true. So what we need to see, incorrect statement. So these are correct statement, this is an incorrect statement. So your option as far as the incorrect statements, that is our answer is, in this case it is D. So these statements are correct, but we have to pick the incorrect one. Okay. So I think it is clear. Just go through once again, and if it is required. Now, which of the following compounds show geometrical isomerism? So to show geometrical isomerism, what is the primary condition is? At a carbon or a sp2 carbon or a cyclic compounds, the carbon must hold two different groups. Then it can show geometrical isomerism. And if they show same at the two double bonded carbons or two carbons in the ring, then the groups at that particular carbon are supposed different. Then we say if the at least one of the group is same, they show cis trans isomerism. Otherwise, they show EZ isomerism. Or we usually say cis trans isomerism also we can apply EZ isomerism, because EZ isomerism is a common or generalized nomenclature, generalized way of saying geometrical isomerism. This is what we follow, priority system, and we say usually. So now, anyhow, I think there is a question for us also, we will see there. So what we see here at this carbons now, at this carbon we have Cl and Cl, the two groups are same. But at this carbon we see hydrogen and methyl. Here also there is a hydrogen and methyl. But this carbon has same groups, this carbon has two hydrogen, this carbon has two deuterium. So in this case, this compound with these two carbons at least now having methyl and hydrogen, two different groups at the particular carbon, they can show geometrical isomerism. So minimum there must be two carbons which are showing this difference in the groups attached. Means if it is one you have only, means you have a 5-membered ring system, you have a methyl group and hydrogen, then this compound cannot show geometrical isomerism. So at minimum two carbons or double bonded carbons, anyhow we will have a two carbons, but in a cyclic molecules usually there must be a two carbons which should have at least the two different groups there. Then they can show geometrical isomerism. So this compound cannot show methyl cyclopentane, but this one can show. So 1,3-dimethyl cyclopentane, or any chlorine also there, that is we will say later. But this compound can show geometrical isomerism. Now whether this one, so again the same, it's a 6-membered ring system, but 6-membered ring system usually exists in the chair form. But at this carbon there is one particular two carbons which are having double bond. You can just usually say like writing like this. They exist in a, just changing a little bit. So you can write a double bond somewhere, or you can write here itself at least, or you can write this carbon better in the plane. That is what we usually do. Clear? But at this particular carbon or this carbon, we have N-Me2 and N-Me2. Clear? So there is a carbon at this corners. Clear? So now what we say, this compound having this carbon with hydrogen and NMe2, this carbon with hydrogen and NMe2. So this compound even can show geometrical isomerism. Okay. Now coming to this, a 3-membered ring system with the 3 cyclopropyl groups attached. So if you take the 3-membered ring system, generally exists in plane. So we say the mostly the groups are exactly opposite to one another like this. Not exactly, but nearly. But at this carbon we have a icyclopropyl, we have, let us say, a cyclopropyl group. At this carbon we have a cyclopropyl group. At this carbon also we have a cyclopropyl group. But if you just change any one of the cyclopropyl group below, so all are on the above to the cyclopropane ring. But if any one comes down, then it is nothing but we have the geometrical isomerism or dipole moment of the molecule or property of the molecule changes or the steric strains are changing. So that this compound with one of the methyl groups, one of the cyclopropyl groups going into the next down or above with respect to the other two. So any one you can change, the other one if you change, both will go down, one will exist above, that's it. So this compound also can show now even geometrical isomerism. But for this compound, at this carbon we have now only OMe, because already 3 bonds are there. This is a double bonded system. This is also having OMe. This group is same, this group is same completely. Clear? So at this carbon we have hydrogen and hydrogens only. At this carbon also we have hydrogen and hydrogen only. Clear? So this compound also has to show, but this is CH2, this is CH2, this carbon has hydrogen. So this compound also at this carbon, there is geometrical, no, he is asking. So geometrical isomerism it can even show. Clear? So coming to the next. An empty slide. This is anyhow what we are actually thought of. EZ isomerism. So when you use the priority system for CIP rules to write at the geometrical carbons, the groups which are having the highest priority, if they are on the same side, then it is called Z isomer. Means if it is a carbon-carbon double bonded system with the two groups are on the same side, 1 and 1 of, this is a pi electron cloud system. So for this pi electron cloud, these two identical priority groups are on the same side or below, then it is called Z isomer. So second priority group, then it is called Z isomer. If it is opposite, then it is called E. So 1 here and 1 here, then 2 here and 2 here. So we have to give the priority at this particular carbons, sp2 carbons. So now coming to the priority system, what we usually say is if the atomic mass or molecular mass is more, then it is given the highest priority. Or if the atom which is first attached has higher atomic mass, then it is given the first priority. Clear? So when the isotopes exist, then the atom with a higher atomic mass is given highest priority anyhow. So here, what are attached at this particular carbon? That is, here the attached atom is first directly attached atom is carbon. So it is having higher atomic mass than this or higher atomic number than this. So this is giving first priority. This is given the second priority. So here also the oxygen is attached. So this is given first priority. This is given second priority. So the first priority groups are always now the same side. So it is a Z isomer. So this is your answer for it. One of the answer. Most of the things are now actually multi-character type. So that everything, let us say mostly covered, that is our intention to pick most of the incorrect like an advanced. So Br and hydrogen, Me and Cl. So here the Br first priority group, hydrogen second priority group, here the carbon first, here chlorine. So here this is a first priority group and this is a second priority. Because the first atom which is attached is Cl. So overall atomic mass is also higher anyhow with respect to methyl. So this is not a Z isomer, it is an E isomer. So this is not our option. Okay. Now coming to this. This is having 3 carbons with oxygen. This has 2 carbons with oxygen. Its mass is more than this mass. So this is a first priority group. This is a second priority group at this. And here also again, let us say this is the 6-membered ring system, 4-membered ring system. This is first priority group. This is the second priority. So this is also set. First priority groups are on the same side and second priority groups are on the same side. But in this case, this is having 1, this is also having 1, or you can't even assign the configuration priority system in this because both these are same. So any carbon which has the same groups, then we say that compound cannot show any type of geometrical, whether it is a cis and trans or whether it is a EZ isomerism, because priority cannot be assigned to these two. Clear? Or sorry, anyhow oxygen is different, no? Okay. So in this case, this is first priority group, sorry, because this is a carbon, next atom is like oxygen. Here it is a carbon and oxygen. It's not overall completely same, sorry. And this is anyhow 2. And in this case, this is again 5. So this is first priority group. This is a second priority. So this one we just try to see in a simple sense. I want to explain in a simple thing, then I didn't consider that point. So here the immediate atom which was attached is carbon, here also carbon, but next immediate atom attached was carbon. So here the next immediate attached is carbon and oxygen. So first atom which is higher atomic mass, that suppose we take oxygen, then here it becomes a carbon and hydrogen. Here also it's a carbon and hydrogens. So whichever comes the highest first preference, higher atomic mass, that will be given the first priority. So this is 1, this is 2. So this is also now again E isomer. So these are the 2 where the configuration is set. Okay. Then let us see the next. Anyhow, I think we have a empty one to explain this. Now, in which of the following the form 1 is more stable than the form 2? So form 1 structures in different options, form 2 structures. So this is now the carbonyl groups both. So one exists like this and another always exists like this. That's okay. That means we say generally comparison suppose is done for this way. Anyhow, that won't exist. C double bond O. Then here at this carbon you can have C double bond O like this. But between these two C double bond O's, usually there is a steric repulsions. So this is not the way in which they should exist. But if this compound you are just doing the enolic form, converting into enolic forms, means this is an enolic form of this actually. So you can write this double bond here and OH group here. Means this type of carbonyl groups doesn't exist. So the other carbonyl group always exists downwards to minimize the steric repulsions. But if you just assume that carbon is existing in the enolic form with the hydrogen of alpha hydrogen coming to this OH group, so this carbon is anyhow sp2. Now it can exist suppose like this. But this carbon you can even write like this. Means this configuration, this orientation you can even suppose assume it like this. C double bonded O. And at this carbon there is again sp2 hybridization like this, and this is an O and H. So between this oxygen and hydrogen there is intramolecular hydrogen bonding. So in the first case there is a possibility of hydrogen bonding, therefore this is more stable than this. So we will say stability suppose. So stability, you write an order, I write here, then we will pick the correct options. So this is more stable than this. So what we have to see is the form 1 has to be more stable than form 2. Okay? So that will not be our option first of all. The next, coming to this is what we say like a pyridine, and it has a OH group at a particular position like 1, 2, 3, 4. So it is like a 4 hydroxypyridine, and it has generally the aromatic character. So generally, usually we say if a ring is like aromatic behavior, it is stable. But this is also still aromatic in nature because nitrogen lone pair exists here. So the aromatic character is not the criteria for these two. This is still aromatic. This is also aromatic because we usually consider only the pi electrons of this part because that C double bond O exists towards oxygen. So that carbon has an empty orbital. So you write C double bond O that side. You will usually say this carbon has like a positive charge. So in the ring completely we have only 6 pi electron system. So this compound is also still aromatic in nature. It's a cyclic conjugated, clear, and having 4n plus 2 pi electrons. This is also aromatic. So both are aromatic. But which form is generally more stable among these two? This form is more stable because even it has the C double bonded O, which has high bond energy. So due to high bond dissociation energy or stronger C double bond O compared to C and O or OH. This form is, we call it as pyridone structure. This is pyridine structure. This pyridone structure is more stable than pyridine structures. So both these, like say this is also like amide, which is also like called pyridone structure. These structures are more stable than these normally because both are aromatic anyhow, but this is more stable than this because of high bond energy of C double bonded O. So in B and C, the form 1 is more stable than the form 2. Okay, and it is, let us say, like a very advanced condition, what we generally consider it exceptional type conditions here. Now what is this now? We suppose see this compound which is written as an enolic form of its diketone forms, but we are writing the hydrogen tautomer from this hydrogen to oxygen here, but we say this CH2 which is present between the two C double bonded O's, which is more acidic. So which hydrogen generally migrates during the tautomerism? The hydrogen which is acidic in nature, that immediately migrates towards it. Clear? So usually even you can say maybe here in this case, even you can say the amide type hydrogens are more acidic. They are more stable. So here the hydrogen which is at this CH2 is more active. So we call it as any CH2 which is between the two electron with drying groups is an active methylene group. That hydrogen generally usually migrates. Or even this compound in this carbon is an sp3 carbon. So there is no possibility maybe for this OH group and this C double bond O groups should exist in the same plane. But in this C double bonded O and this C OH group all exist in the same plane because this is sp2 carbon, this is an sp2 carbon, this is an sp2 carbon. So this C double bond O and OH groups both are existing in the same plane, then they can show easily the intramolecular hydrogen bonding. And this carbon-carbon double bond which is there here has more, let us say, hyperconjugatable hydrogen with respect to this CH3. So because of this, we say the tautomerism should not be done from here to here. So we have to be it should be migrated from this active methylene carbon hydrogen, not this terminal carbon hydrogens. So this form is more stable than compared to this enolic form. So this enolic form is more stable compared to this enolic form because of hydrogen bonding exists, and the migration should not occur from there, it should occur from the middle. So this is also less stable, this is more stable. So your options are as far as the B and C, where the form 1 is more stable than the form 2 because of high bond energy of C double bond O, as well as there is aromatic nature in it. Okay, coming to the next question. So let us see some integer type questions or numerical based questions also you are usually getting in the advanced. So how many isomers that exist? So he said stereoisomers that exist. So let us see the compound, already are seeing it. Can we have geometrical isomerism at this? Yes. And since anyhow this carbon has hydrogen, this carbon has hydrogen, we can have even cis trans here. And even cis and trans at this. As well as we can have E and Z also. So, but you should not count 2 times cis trans separately and EZ separately. Your cis may become E, your trans may become E, depending on the priority systems. Here, anyway, in this case now hydrogen and hydrogens are there. So cis form becomes Z, trans form becomes Z, E. So cis is nothing but Z, trans is nothing but E, because anyhow this carbon has phenyl group and hydrogen. This carbon has hydrogen and this side completely cyclic cyclohexane group. So it is anyhow cis will become always Z, trans will become E. But you should not say trans is always E, cis is always Z. Because of the priority system, the EZ nomenclature is different from cis trans nomenclature. So here also same, E and Z can also exist. Only to write easily that what we said, E and Z and trans instead of cis trans. But this carbon, which is a 6-membered ring, has hydrogen here and hydrogen here. So we are checking just simply the geometrical isomerism itself. So when you write different geometrical isomers here, there may be some optically active compounds in it, optically active molecules in the cis trans itself. So sometimes we say cis is active, trans is inactive, like of center of symmetry that exists, and a plane of symmetry that may exist in cis compound or trans compound. That's why they may become optically inactive. So cis is optically inactive, trans is optically inactive. Everything we usually apply. So now let us see at this carbons what we can write. So I just check like this. This is suppose E. Means let us say at this ring system, mainly at this carbon and at this carbon. Let us say it is like a cyclopropane, cyclohexane, we write only chair form or that axial and equatorial bonds. But anyhow, axial and equatorial bonds are like this. So you are just saying this axial bonds are, so at this carbon, this is the first carbon above, at this carbon, this is below. You can usually say like that also. So this is axial above, this axial is below. So the other part will become equatorial. So simply write like this. Now check like this. So there is a carbon double bond systems like this. There is a carbon double bond system like this. Clear? So here we are writing the hydrogens may be like this. Then there is a methyl group like this. Here we are writing hydrogen like this, hydrogen like this, methyl group, phenyl group like this. Now you can interchange this instead of disturbing this chain. Now you can write this downwards and this you can keep it up. So this complete carbon-carbon system, it will become like a cis or trans type. or E or Z type at this stage, because you have hydrogen here and hydrogen here. So here also you can use cis in this ring system totally. So suppose at this carbon center, means let us say this carbon center as or stereogenic center as, this stereogenic center is 1. So one stereogenic center, this is the second stereogenic center, this is the third stereogenic center. And anyhow, it's a simple formula what we write. Their stereogenic centers, this part is not same as this part, and your terminal parts are also not same, methyl and phenyl. So simply you say total number of geometrical isomers or stereoisomers are nothing but 2 to the power of n. That is 2 to the power of 3. In this case, there are 3 stereogenic centers. We say it is 8. It's a simple way, formula based, at least if you understand it or visualize that molecules, then it is a simple way to write with respect to the formula maybe. So this is one stereogenic center, another stereogenic center where geometrical isomerism can exist. Here also there is another stereogenic center where the geometrical isomerism can exist. So number of stereoisomers, whether it is optical or geometrical, all you can count at one place. So now here, instead of that, let us check like this even. You write like this. At this you are writing E. At this you are writing E. At this you are writing E. Let us say this is the first one. What we can do is, at the first one, you can keep the configuration of that same. You can change the configuration at the second and third, or second and third stereogenic centers. So how many we can have? Let us say E. I can have E and this is Z. Then third, you can have E. Here you can have Z. Here you can have E. Then fourth, you can have here E. Here you can have Z. Here you can have Z. Or cis, like that also. Trans, cis, trans, like that. But instead of that, it's a better way if you check through E and Z, because all the stereogenic centers can show and they are different from one another, and symmetry will not be there. But suppose one of that is methyl, then we say the different one, because at this you write E, at this you write E. When you interchange them, they are same. Like Z, let us say only one middle carbon affects it. So Z, we are writing E, suppose E, Z, E. We write at third to first, then it is E, Z, E will be one and same. Or E and Z, Z and E will be the same. So at 1 and 3, E and Z or Z and E will be one and same. Only that it change with respect to the 2 actually. If they are same, if this side you have methyl or this side you have phenyl. But now they are completely different. So we fixed 1 and we have written 4. You fix the Z at the 1, you can write another 4. So total number of isomers will become now 8. Okay. Now coming to the next question. So the number of keto groups in the stable keto form of the following. So all these OH groups are completely having the interactions. So in the plane completely, but these interactions, OH interactions, instead of that, you can have the stable keto form for this. What you can see? Any one of that OH group you can just suppose convert into keto form. Means this hydrogen you are bringing and writing this C double bond O, you are bringing and giving it to this. So what you can write, suppose the keto form of this. So you write a keto, this is an enol form. What is its keto form you can write? We say this is a C double bonded O. This carbon will be OH. So this carbon has hydrogen, because the hydrogen comes at this carbon. Now at this carbon, immediately write C double bond O alternatively. and this carbon will be remaining as still OH, suppose. And at this carbon again, let us say C double bonded O and OH. So this is its keto form, which is a stable one. Because between any C double bond O and OH groups, there is intramolecular hydrogen bonding. So what we see, if you write a stable keto form, means if you write one of that itself into keto form, keeping the others in the enolic form itself, that is not a most stable form. Because when you write completely all into the keto forms, possible number of keto forms, all you can't convert any of. Because if this OH group comes here, hydrogen, then this hydrogen cannot tautomerize later. Clear? So this hydrogen is tautomerizing there. So this is becoming sp2, sp3 later, or this carbon may become sp3. Maybe you can write here, but you can just write even this part. Why can't you write like this? You may write even, suppose like this. You can say this remains as OH. This, clear? This C double bonded O comes here, then this is C double bonded O. Clear? Then among this one of that you can just do. But anyhow, instead of having this C double bonded O in the alternative position, what it will give? The hydrogen bond possibility increases on the two sides. And this form becomes more stable compared to this. Clear? Or even if you write a C double bonded O here, any one of that will become suppose C double bonded O and OH group. Between this C double bond O, this C double bond O, or when you are writing this C double bond O here, between this C double bond O and this C double bond O, there will be again repulsions. So both the groups should not come on the same sides. So that this keto form is alternative positions is more stable than this type of keto forms. So in any keto form, you may be having only three possibilities. So the most stable keto form is this, and which has totally three keto groups. Okay, I think it is also clear. So how you just try to see a tautomer into the other forms is mostly try to bring them into the mostly the stable forms which has an intramolecular hydrogen bonding and all that, or Neumann projection isomers into the having the intramolecular hydrogen bonding, that what we covered, staggered forms, partially staggered forms where the intramolecular hydrogen bonding can exist, they can stabilize it. Okay. So now coming to this little bit of electronic effect applications here. So which of the following structure is true for the stability? So which is, this is a stable or this is a stable? So anyhow, when we just see the stability, here there is all are like oxygen with negative charge or oxygen with negative charge. But anyhow, there may be another possible structures where sometimes oxygen may have negative, carbon may have negative. So instead of let us say only seeing this, which type of resonance structures you generally see? Because these are not resonance structures actually. Anyhow, maybe it's not resonance structure, they are isomeric structures. Because instead of existing the double bond here, you are having the double bond here in this. But usually the atom position has changed. Then we don't say them as resonance structures. So only in the resonance structure, electron cloud only will be my, let us say, delocalizing. But here the atom positions has changed. So they are not resonance structures. But in a resonance structure, which structures are generally stable? The structure where the octet system exists first. Even though the charges might be there. But where the structure with the octet nature exists. That is all atoms except hydrogen. Like atoms which are possible for us in an organic compound is like carbon, oxygen, nitrogen, sulfur, phosphorus, halogens, where the octet nature exists. such type of species, resonance species, which are more stable compared to others without octet nature. Means we just usually simply see there is CH3, CH plus and NH2. But what is its resonance structure? You can write it. This nitrogen lone pair immediately can be delocalized because it is present in an immediate position. That empty orbital with their carbon with the positive charge is nothing but empty orbital. So this carbon with empty orbital, this nitrogen lone pair immediately delocalizes or gives its lone pair into that empty orbital. So that CH3, CH double bond NH2 plus. Usually we say nitrogen is more what is usually? Nitrogen is more electronegative than carbon. But generally electronegative atom should have negative charge and electropositive atom should have positive charge. But both the species are having the charges. So in such case, what is the first priority or the first rule that we should follow? That is, the structure with octet is more stable than structure with even charges. So in that preferential order, if we go, so if a structure is there with all structures are having octet, then we see a structure without charges. So a structure without charges is more stable than the structure with charges. But everything should have an octet first. Then if suppose all structures are having the charges and all are having octet, means first octet, then all are having the charges. So there is no structure without charges, no polar group. So then what we see, the structure where electronegative atom having the negative charge is better than the electropositive atom having the negative charges, or the reverse case. Electropositive atom, if it is a positively charged species, electropositive atom should have a positive charge and electronegative atom should have negative charge, or it should not have a negative charge, positive charge. Sorry. So electropositive atom having a positive better than electronegative atom having a positive. Means if both these structures are having octet, suppose, then this structure is less stable, this structure is more stable. But here this has 6 electrons, this has 8 electrons. So this one is more stable even though the nitrogen has a positive charge. So what we see now is, here anyhow that is not it, and the next two part, what is that resonance structure we complete, then we will come to this question. So after the seeing the charges, electronegative atom has always negative charges suppose. Then the positive and negative charges suppose there are identical charges are there, they should be away. Similar charges are there, they should be away. Opposite charges are there, they should be closer. So that one minimizes the other, one compensates the other. So positive charge compensates the negative, negative charge compensates the positive. Or more electron denser groups should be away and electron denser and electron deficient positions should be closer. So this is how we follow the resonance structure stability order. Octet, then no charged structures. Then we follow the charges should be on the electronegative atom with negative charge and electropositive atom with positive charge. And the charge separation should be less. Or the electron deficient species should be far, electron rich species should be far, but electron deficient and electron rich species should be closer. So now what is in this case? So this carbon has a double bond here, but this carbon now with a double bond has hyperconjugatable hydrogens. But here there is hyperconjugatable hydrogen only one. So one hyperconjugatable hydrogen, here 6 hyperconjugatable hydrogens. And both these cases oxygen has negative charge. So we will say stability wise, this is wrong, this is more stable. So this is not our option, because which is true we have to pick. Next, this one. Here this carbon double bond, this radical, all are in continuous conjugation. But here you can write the conjugation, resonance, but this negative charge will come like a pi bond here. This carbon pi bond, one of the pi bond electron comes as a double bond to form double bond here. So what you will write a resonance structure of this is, you write CH2 double bond C, CH2 dot, CH double bond CH2. Means you can write only resonance between these two, or you can write resonance between these two. But this has an extended conjugation. Means this negative charge, pi electron can go towards this, then dot can exist here. This can go like this. So this odd electron carbon, odd electron on this carbon can move on to this total molecule, so that it will be continuous conjugation, extended conjugation that exists. That's why this is more stable than this. So this is greater than this, which is true, okay, for us. Okay. Next, coming to this thing. Again, this double bonded, this is primary carbon, this is also primary carbon with a positive charge, so primary carbocations. But double bond is in conjugation here, double bond is in conjugation here. But this double bonded carbons having methyl group here, here it has a methyl group here. Clear? So now what you see is this structure comparison is hyperconjugatable hydrogens are same. Clear? Everything same nearly. But only thing is this positive charge can move to this carbon, but this CH3 group is closer to CH3. So the plus I affecting group is closer to that double bonded. So this is like what we say allylic. This is what we say allylic. The CH2 double bond CH2 plus. But the plus I affecting group is closer. Here the plus I affecting group is. So we say this is again correct. So plus I affecting group is suppose closer. Then it gets stabilized. So here this is now negative charge can move from oxygen to oxygen in this. But here the negative charge is delocalized, but it moves on to the carbons. Clear? So that what we see, this one is negative charge is delocalized from oxygen to carbon. This is less stable and this is more stable, and you even say there is a part of like a resonance. We call it as a grade 1 type resonance, where the charges always are two structures or three structures, what we write resonance structures, they are identical structures. Then what we call it as a grade 1 resonance. What is the other one? If a negative charge or charge is going from one atom to the other atom, a different atom, then such type of resonance we call it as grade 2 type resonance. And if the charge is not there, due to the resonance you are getting the charges. Maybe if you take the example here, we can take this example and say as a grade 1 or is grade 2 or grade 3. What is grade 1 meaning? Is suppose you have an acetate type or R C double bond O minus carboxylate ion. The negative charge can delocalize and will give identical structure here. So this is like a grade 1. What is grade 2? That is already we have phenoxide ion there. So the phenoxide ion, the negative charge on the oxygen is delocalized towards carbon. Double bond O. So this can delocalize to this. This can delocalize to this. At ortho para positions, you will get negative charges again while doing the resonance. So here, this is now suppose take as for the grade 3. You take simply phenol. the oxygen lone pair can delocalize towards the carbon ring, double bond OH plus, this O minus. What we see? This is a grade 3 where the charges were not there in the original structure. Due to the resonance, we are getting the charges. So what we say, the stability wise, grade 1 is more stable than grade 2 type resonance, is more stable than grade 3 type. That's why we even say like the carboxylate ion is more stable than carboxylic acids. Because even in the carboxylic acids, you have grade 3 resonance, that is R, C double bond O, OH. This oxygen lone pair can delocalize like this. So you will see R, C, O minus, double bond OH plus. So carboxylate ion is more stable than the carboxylic acids. Clear? So grade 1 is more stabilizing than grade 3 or 2. That is, even we say carboxylic acid and phenol. If you say carboxylic acid is more acidic than phenols. So we say the grade 1 is stabilizing this more, grade 2 is stabilizing this less. That's why the conjugate base of carboxylic acid is more stabilized than the phenol conjugate base. So this is also what we can use in an acidic and basic strengths as an application, and phenoxide is more stable than the phenols. Okay? So that is usually what we consider it, but these are not resonance structures. Sometimes you already said negative charge is more, let us say neutral is more stable and negative charge is less stable. It's not normal. It's a resonance structure where the stability what we applied. Okay. So here, this is anyhow more stable than this. Clear? Okay. Coming to the next one. So in which of the following pairs there is a less resonance energy? So what is meant by less resonance energy? When there is more resonance, then there is more stability. Means which will stabilize, which are stabilized, that will have very high resonance energy. Which are less stabilized, they will have more, very less resonance energy. Means we just usually say the resonance energy is the part of energy which was utilized for the delocalization of electrons. So the resonance energy generally we try to write in the form of positive, which is utilized. You can write negative, that is also last, like that also you will see. So when there is more resonance, the molecule loses more energy, then it becomes more stable. But resonance energy we generally usually write the energy which was utilized for it or used for it. Generally we say like positive forms. So resonance energy of benzene and everything. But there is, even you can write a negative. But what we usually conventionally follow. So what is now we will see. This one has more resonance here because the delocalization happens here like this. Continue. So how many structures you will get that like that? You will see this negative charge can delocalize to this carbon. Then from this carbon it goes to this carbon. Means if you are getting the final structure, suppose like this. That is, this oxygen negative charge converted as a double bond here. This pi bond is initially converted as negative charge here. But this negative charge again converted as a pi bond here. You will get negative charge at this. So you had a negative charge first at this carbon. We had negative charge at this carbon first initially. Let us write this. We had negative charge at this carbon first. Then we got the negative charge at this carbon. We got negative charge at this carbon. But here, if you do delocalization again, then you will get negative charge at this. Because we have seen this type of question, which is suppose the cyclopentadienyl carbon anion. Cyclopentadienyl carbon anion has how many resonance structures? So generally we do is we write from ortho position, alternative position, we just go on and do and write 3 structures. No, because this carbon is getting negative, but this carbon after negative, this can go out on this, means this carbon also can get negative, and even this carbon can get into. That is what we write usually cyclopentadienyl carbon anion, negative charge we write like this. So it is delocalized on the all 5 carbons. So we say this compound is now having the 6 pi electron system totally, because the negative charge is converting. This is aromatic. But this one, which is sp3 carbon here, and the negative charge can delocalize between this carbon to this only. So there is not a complete resonance in this, in the ring. That's why we say this compound is not aromatic in nature. So the compound which is aromatic, means the structure species which is aromatic, gives more stability. So then it will have more resonance energy. So the pair where the compound 2, the 2 compound they said, so this is first and this is second, okay. So compound 2 has less resonance energy. So this has less resonance energy, this has more resonance energy. So our option can be 1 first. Now coming to this, here there is completely Benzian ring resonance exists, but this is now aromatic again, but this is not aromatic again, non-aromatic. So this has clear less resonance energy. This is also true, because more resonance energy is there in case of, let us say, the aromatic systems. Because of aromatic character also it comes more. So next, coming to this is again, you see the pi electron cloud systems completely opposite. Here the pi electron systems are away closer. So there is a steric repulsion between these two. But this also has now resonance like this. Pi bond comes like this, pi bond shifts like this, pi bond again can shift back and can go like this. So it happens completely. But this C double bonded O, this C double bonded O groups completely opposite. But these are closer here. There is a steric repulsions. So this carbonyl groups should never exist like this. So this has more resonance energy, this has less resonance energy. Because during this there is less steric repulsions. So here again this nitrogen lone pair is there, which is in conjugation again. Here this oxygen lone pair is there, which is also in conjugation here. Both the compounds are aromatic, pyrrole and furan. But what we see, the nitrogen delocalization is more than oxygen delocalization. So why nitrogen delocalization is more than the oxygen? Because nitrogen to carbon, the overlapping ability is high according to the VBT theory, valence bond theory. So what we say, according to VBT, why the carbon nitrogen pi bonded or delocalization is better than carbon and oxygen. So according to the VBT theory, if the electron energy difference between the 2 atomic orbitals is less, means if the energy difference is less, then the overlapping ability increases. So between the carbon and carbon, the overlapping ability is more than the carbon and nitrogen, and which is even more than carbon and nitrogen is more than carbon and oxygen. So even we apply this also in case of the same like fluorine is there on the benzene ring, activating group, deactivating group applications. So halogens are called deactivating groups. But why fluorine behaves like a more activating group than chlorine? Because the fluorine lone pair, when it is delocalizing, it's the overlapping of the 2p orbital of fluorine and a 2p orbital of carbon. but when the fluorine lone pair is delocalizing, then it is the chlorine p orbital, that is the 3p orbital with the 2p orbital of carbon. That is why chlorine is less activating, means otherwise ortho para directing, means in the order increasing order of deactivating actions. If you see fluorine first, then chlorine is more deactivating, then bromine, then iodine. So there also we do that applications. So here the nitrogen delocalization is more than oxygen. That's why this has more resonance than this. So this has more ability to undergo resonance compared to this. This is also true. Clear? So this is how we can see the applications, and the some aesthetic strengths we even discussed here. Clear? And some electronic effect applications, resonance energy applications, some isomerism related things. So much will be there for us, and to the extent that we can cover, that we try to do, and we tried now, and let us see, and in the next session we will end this session with this now, and okay, all the best. Thank you. We will see in the next class.